Hi everyone, welcome back to our series on vectors. This is episode number 2 and we'll be discussing projections and various applications of vectors in exam style questions. So in this episode we'll be discussing 3 topics. 1. Projections, 2. Geometrical applications, and 3. Applications involving motion and forces. Projections occur when we project one vector onto another vector, like how a projector works or how we create a shadow on the ground. So, say we want to project the vector u onto vector x. The projection represents the part of the base vector x that the projected vector u lays a shadow upon. More specifically, we draw perpendicular lines from the base vector to the projected vector, and thus AB represents our projection. The length of AB is called the scalar projection, where comp stands for the length component of vector u on x. The actual vector AB is called the vector projection. The notation is similar to how we write logarithms, where u represents the vector we are projecting and x represents the base vector we are projecting on. Now, for us to derive a formula, let's draw an equivalent vector u so that the tails of the two vectors meet. This will create a right angle triangle, and using basic trig, we can calculate the length of the projection. Hence, the scalar projection is equal to the length of u times cos theta. As the length of a unit vector is 1, we can multiply it without changing the value of the expression. The reason why we do this is because whenever we see cos theta with vectors, we always want to try and relate it to the definition of a dot product. That expression is just equal to the dot product of u and the unit vector of x. Now, the vector projection represents the whole vector AB, and we can observe that vector AB is just the scalar multiplication of the base vector x as we are going in the same direction. So, if we have the unit base vector x hat, then we just need to figure out how many x hats we need to produce the vector projection. Since we figured out the length of AB already, we can just multiply the scalar projection to x hat. So, using the same working out for our scalar projection, let's just multiply x hat to each line. These expressions of the vector projections are in terms of the unit base vector x hat. Substituting the definition of a unit vector, this is the expression in terms of the base vector x. Now, let's look at a question about geometrical applications of vectors. Question number 1. Using vectors, show that a line joining the midpoints of a triangle's two sides is parallel to the third side and half its length. This is a classic exam question where it tests our understanding of both vectors and geometry. Especially for vectors, we need to first start off with a clear diagram. So let's draw a triangle with points O, A, and B. Let's also label the midpoints as M and N. We just need to prove that MN is parallel or going in the same direction as AB, and that MN is half the length of AB. Therefore, we are required to prove that vector MN is equal to half of vector AB. Let's start by labeling the position vectors OA as vector A and OB as vector B so that we can express other vectors in terms of A and B. Now, here is an awesome tip. Because vector addition adds head to tail, we can essentially split vectors with a common point. In this case, we split vector AB with the origin into AO plus OB. Then we can reverse the direction of AO by negating the vector to OA. Since OA and OB are position vectors, vector AB is equal to vector B minus vector A. This formula is very useful to memorize. Any vector is equal to the subtraction of the head position vector to the tail position vector. Now let's try to find vector MN. OM is equal to half of vector A because OM is half the length but in the same direction as vector A. Similarly, ON is equal to half of vector B. So vector MN is the subtraction of the position vectors ON minus OM. Now, comparing the vectors MN and AB, we can deduce that vector MN is actually half of vector AB. Question number 2. Under which conditions are two vectors parallel or perpendicular? To observe if two vectors are parallel or perpendicular, we can look at the angle between the two vectors. And as soon as we mention angles in vectors, we must immediately recall the dot product. So if the vectors are perpendicular, then theta is equal to 90 degrees, and hence the dot product is equal to 0. Another fancy way to describe perpendicular vectors is by calling them orthogonal. For example, our basis vectors I and j are orthogonal, and the dot product will be equal to 0. Now, if vectors are parallel, then theta is 0 degrees if the vectors are in the same direction, and 180 degrees if they're in the opposite direction. Recall that the direction cosine is equal to the dot product of the unit vectors. So if the vectors are parallel, then the dot product of the unit vectors are equal to plus or minus 1. Motion can be defined as movement of an object with respect to time. We are probably familiar with using scalar quantities such as distance and speed. However, we must include a direction for vector quantities such as displacement, velocity, and acceleration. A classic question will involve a plane flying in the sky with a crosswind or a boat sailing in the river through a current. For example, an airplane is flying at a velocity of 160 km per hour east. However, there is a strong wind with velocity 80 km per hour blowing in the direction south 30 degrees east. What is the final resultant velocity of this airplane? So again, let's first draw a vector diagram where vector Vp represents the plane's velocity and vector Vw represents the wind's velocity. It is convention for north and east to be positive directions. So we just need to add the two vectors to find the final velocity of the plane. Resolving into components, the plane's velocity can be written as 160i plus 0j, and the wind's velocity is 40i minus 40 root 3j. Finally, we just add the horizontal and vertical components separately to calculate the final velocity vector as 200i minus 40 root 3j. We usually don't represent velocity in vector form, but rather in its magnitude and direction. So to find the magnitude, we find the length of the vector using Pythagoras, and for the direction, we find the angle using trig. We can calculate theta as 19 degrees, so the final resultant velocity of the plane is 212 km per hour south 71 degrees east. The physical world is full of forces that act upon objects. All forces are vector quantities, so they must be stated with magnitude and direction. There is a famous law in physics called Newton's second law, which states that the net force an object experiences is equal to its mass times its acceleration. Even if there are multiple forces acting on the object, we can calculate the net force using vectors. So there are many different types of forces, but we'll just introduce the main ones. And please note that motion and forces will be covered in depth in the mechanics series. Weight force is a force exerted on an object due to gravity. On Earth, the weight of an object is equal to its mass multiplied by the acceleration due to gravity at 9.8 meters per second squared. Normal force is a reaction force exerted on an object by the surface, and it is exerted perpendicular to the surface. Friction is a resistive force exerted on an object as it moves along a surface, and it is exerted in the opposite direction to motion. Finally, tension is a force exerted on an object through a rope, string, or a wire when pulled on both opposite ends. And tension is exerted away from the object through the rope. So to answer questions on forces, we just need to draw a free body diagram and label all the forces acting on the body. Then, like all applications we've been doing the entire episode, we just need to resolve and add forces with vectors. There will be a bonus episode on a force application problem involving King Sisyphus in Greek mythology, where he had to roll up a boulder on a hill for eternity. So that's it for episode number 2. We've scoured through vector projections and various applications using vectors. So like, subscribe, and leave a comment down below on what you would like to learn about. I'll be there.